Okay, so today we're going to talk about let me share my screen. So today we're going to talk about how we do programming on the Pentium CPU and assembly programming in general. Still, we are in the process of this is week number 9. Yeah, we are in the process of discussing what is a program. Again, by now I think you all know a program is a sequence of steps. For each step, an arithmetic or logical operation is done. For each operation, a different set of control signals are needed. As you recall, we said that the CPU is consisted of registers, an ALU, and a control unit. So the control signals are provided by the control unit. The arithmetic and logical operations are done by the CPU. The data needed for these operations is basically stored in the registers. And finally, in order to have a proper sequencing, we have something called the program counter or the program counter, or it's the program counter basically, or the instruction pointer as the other books try to call it. So the function of the control unit, for each operation a unique code is provided. Now the add operation will have a different code than the move operation, than the jump operation. So a hardware segment that accepts these codes and issues control signals will build a simple computer or a processor. This again, if you go to the emulator that you are using in the lab for a simple program, you can see that if I start with origin 100 hexa, I will just write a move to AX, 0D31C hexa. Then I will add AL, BH, and then I will, if I just run them, I just want to show you that you can see over here that this move instruction has B8 as its function, and the next instruction, which is the add, is 02 as its operation code. 02 as its operation code. So each instruction has its own code. So the components that are used are the control unit and the arithmetic and logic unit inside the CPU. The data and the instructions need to get into the system, and the results need to get out of the system. Temporary storage of the code and results is needed. This is basically the job of the main memory or the RAM.
Victor, please record the session.
It is recorded as usual. I record the sessions and upload them after class. I don't record using Microsoft Teams. I record using another program. Anyway, if you are attending, no need to record it unless you are sleeping inside the session. So computer components in a different level. Once more, you have your CPU, you have your main memory, which is the RAM, your CPU, and you have your input-output devices. Now inside the CPU, you have your execution unit, which is the ALU. Inside here, you have the program counter, you have the instruction register, you have the memory address register, you have the memory buffer register, you have the input-output address register and input-output buffer register. These are all simply basic registers inside our CPU, and the CPU usually holds more registers, but it depends on the structure of the CPU. But these are the basics. The important ones are the program counter, instruction register, and the execution unit. Of course, inside the CPU also we have more registers, which are the general purpose registers such as AX, BX, CX, DX, and the special purpose registers such as the code segment, data segment, the segment registers, the pointers, the stack pointers, and the program flag registers. So when it comes to an instruction cycle, and this is our focus for today, usually we think about it as a two-step cycle, which is fetch and execute. So what do we fetch? We fetch the instruction. From where we fetch it? From the main memory. How do we fetch it? Using the instruction register, using the program counter. The program counter, as you recall, it points points to the next instruction to be executed. Okay, next instruction. يعني the program counter does not hold the current instruction, it holds the next instruction. So you start your cycle with the start, then you fetch the next instruction, then you execute the instruction, then you go once back more and fetch the instruction once more. This will take the CPU into an infinite loop unless something else happens. If your CPU is in that infinite loop, then it's called the fetch execute cycle. Inside the fetch cycle, the program counter holds the address of the next instruction to be executed. The processor fetches the instruction from the main memory location pointed by the program counter. Then we are going to increment the program counter unless told otherwise. Why unless told otherwise? Usually each instruction will increment the program counter. لأنه again the program is a sequence of instructions. So I'm executing instruction 1, then instruction 2, then 3, then 4, then 5, then 6, and so on. However, if I face an instruction such as a jump instruction or a loop instruction, then I will be in I'll be in a different story where I will be not incrementing the program counter. Now, instructions loaded into the instruction register, the processor interprets the instructions and performs the required task. This is the job of the decoding stage. In the execution stage, the processor and memory, the data is طبعا يعني to understand it, not all the executions are the same. Some executions include the memory. Some executions include the registers. يعني if I say move AX, A, معناته go to the memory location specified by A and move the contents into A. So this is a processor memory instruction. Data transfer between the CPU and memory. Sometimes it's a processor input output where you transfer the data between the CPU and the input output. If you want to display something on the screen, then you are going to use this instruction. Some instructions use data processing such as arithmetic or logical. Other instructions such as the control instructions, they alter the sequence of the operations such as jump, and you may have a combination of the above instructions. So the execution depends on the type of the instruction. The execution, it's not the same. مش مثل الفetching where I will say it's okay, go to program counter, fetch the instruction, increment the instruction, decode the instruction, send to the execution stage. Inside the execution stage, it all depends on the type of the instructions. Some instructions will require memory, other instructions will require only the CPU data, some instructions will require arithmetic and logic operations, other instructions will be control instructions where we usually deal with jump and loop and call and return, all of these control instructions. يعني any instruction that deals with the program counter is considered a control instruction. Now the instruction or each instruction has a format, and I think by now you understand what's the instruction format. The instruction format has a part which is called the opcode and another part which is called the address. It depends on the type of the instructions. This will be explained more in the architecture class, inshallah, next semester. The integer formats, usually the leftmost significant bit is considered the sign bit. If it is 0, then it is positive. If it is 1, then it's a negative number. You have here your program counter, instruction registers, and your temporary storage, which is the accumulator. And this is your different functions such as load accumulator, store accumulator, and add accumulator. This is all seen in the tutorial. I think if you check this example, we start at program counter equal to 300. At this 300, we go and fetch the instruction which is in memory location 300. So the instruction is 1940. In the execution stage, we try to understand what's 1940. 1940 basically is 1, 2, 3, 4, 1, 2, 1, 0, 1, 0, 0, 1, and 0, 1, 0, 0. This is the 1940. So this is our opcode. Now, since this is our opcode, we are going to try to see what is 001. 001 from here, it is load accumulator. So I'm going to load the accumulator with the memory available in memory location 940. So I will go to memory location for 940 and take whatever is there and send it to the accumulator. At the same time, I'm going to increment my program counter. My program counter is 301. For the next instruction, which is 301, I'm going to load the instruction which is 941. So we are going to see what is 5, which is 0101. We will go to the instruction over here. So it is add accumulator from memory. So I'm going to add whatever is in the accumulator to whatever is in memory location 941. So what's 941? It is the value 2. So I'm going to add 3 plus 2, and which is equal to 5, and store the result into the accumulator. And at the same time, I'm going to increment my program counter. Then we are going to fetch the last instruction, which is 302. It contains 2941. The 2, so the most significant bit is 2. I'm going back here. 2 is store accumulator to memory. So I'm going to store whatever is in the accumulator in memory location 941. So 941 will contain the value of 5. I think in the tutorial you already had some example like this. This is just an explanation to see how things are going. Now the instruction cycle and state diagram. This is just to show you how the instruction cycle is operated. So usually, where is our starting point? Our starting point is over here at instruction fetch. I fetch the instruction, then the instruction operation is decoded. Decoding the instruction is trying to open what's inside the instruction and understanding the operation behind it. Then we are going to say, we are going to do operand address calculation. Where are my operands? The operands can be either in registers or in memory. Sometimes the operands, again, depends on the addressing mode. You remember we said there is direct, there is immediate, there is indirect, and different addressing modes. So if my operand is a direct operand, then it's fine. If it's indexed, then we do some calculations. We go and fetch our operands. Once the operands are fetched, we do the data operation, whether it's addition, subtraction, multiplication, and or logical operations, shift right, shift left, any operation is there, we do the data operations. Then we go and calculate where we are going to store our operands. So we need the result, we need the address of the result. Sometimes you need to calculate it, sometimes it's already over there, or basically the destination. Then we go and store our result. After the result is stored, we go back and check our instruction address calculation or our program counter. So this is basically the instruction cycle state diagram. It depends on different instructions and different cycles, but it's quite all straightforward. Now, above all of this comes something called the interrupts, which are very important inside the computer system. Interrupt systems basically interrupt this cycle. This cycle, if a computer only works without interrupts, then we have a problem, because interrupts can save the computer and can help the computer handle very difficult problems. So interrupts are mechanisms by which other modules, such as input-output modules, may interrupt a normal sequence of operation. Now, when you say an interrupt of a program, usually interrupts are for things that are very important. So you interrupt a program because there is an external event that cannot be cannot wait. Your computer needs to handle that interrupt. In a computer system like we are using right now, if I move the mouse, this is an interrupt signal. The computer cannot always wait for keep asking the mouse, are you moving or not? But once the mouse is moved, the computer will do what? The computer will basically service that interrupt and reads the interrupt values. Some interrupts happen from programs such as overflow or division by 0. Other interrupts happen from timers, and timer counters are very important. We are going to study them inshallah in the embedded system class. These are generated by internal processor timers and used via primitive multitasking fashion, which we are going again to talk about in the embedded system class. Then we have some interrupts which happen from input-output, and some interrupts happen from failure in memory. But when an interrupt happens, how do we deal with it? This is the main question. If an interrupt happens, we need to understand the cycle of the interrupt. Now, an interrupt is added to an instruction cycle. The processor checks for an interrupt indicated by an interrupt signal. If no interrupts, the fetch the next instruction. Yani after you finish an instruction, you are going to check for interrupts. You cannot interfere the instruction in the middle and say there is an interrupt. Yes, there is an interrupt, but the current instruction needs to be finished. Then we can service that interrupt. If interrupt is pending, we are going to suspend the execution of the current program. Suspend mean stop it. Save the contents of all registers. Usually we do that by pushing the register values into the stack. We take all the registers, we push them in stack. We service the interrupt, and then we take back all the data from the stack. Now set the program counter to the start address of the interrupt handler routine. Now once you get an interrupt, that interrupt will direct the program to a new small interrupt service routine. This interrupt service routine has an address, so we are going to load that address into the program counter. Then we are going to process the interrupt and finally restore the context and continue the interrupted program. So this is basically what we are doing. Device or device controller or hardware system issues an interrupt. The processor finishes the execution of the current instruction. The processor signal sends an acknowledge. Yani I request an interrupt, the processor will send me back an acknowledgement that the interrupt is okay, you can start with the interrupt. So once the interrupt is acknowledged, the processor is going to push the processor status word. Now this processor status word is basically all the register values. It has all the AX, BX, CX, DX, everything, all the data is going to be pushed inside the stack. Push is usually used as a stack verb. So it is going to be pushed, and the program counter and the control stack, everything into the stack. Now the processor loads the new program counter value based on the interrupt. The save the reminder of the processor information, process the interrupt, restore the state information, and restore the old program counter data. Yani you are running a program, an interrupt signal comes, the CPU will send an interrupt acknowledge, and then it's going to push the processor status word and the program counter into the stack. It is going to load the interrupt service routine. It's going to load the interrupt service routine address vector into the program counter. Then the CPU will process that interrupt. Once the interrupt has been processed, the CPU will pop back the processor status word plus the program counter, so that the old program can resume and come back and continue its execution. So basically this is what's happening. You have your user program over here. So once an interrupt happens, we are going to go and service that interrupt, and when we come back, we want to come back over here at the same point as to act as nothing has happened during the interrupt part. So this is the instruction cycle with the interrupt. So you start, you fetch a new instruction, you execute the instruction. Then after that, if the interrupts are disabled, you continue at the same way. If the interrupts are enabled, you go and check for interrupts. If the interrupts are there, you are going to service them. Then you are going to go back and fetch a new instruction. So you do not check for interrupts over here. You do not check for the interrupts in the middle of the processing. You check for the interrupts at the end of each cycle. Now this is the instruction cycle with interrupts. So the instruction cycle with interrupts, as you can see over here, we start at instruction fetch. After we fetch the instruction, we need to find, do a decoding, calculate our operands and addresses, fetch our operands, do the execution, calculate where to store the result in the destination, store the result, so everything is done. Now here we check for interrupts. If there are no interrupts, we go back to the beginning. If there are interrupts, we service the interrupts, then we go back to the beginning. So this is the extra added part for your interrupt system. This is the flow diagram of control system, and in this flow diagram, as you can see over here, you have a program which has no interrupts, and as you can see in this program where there are no interrupts, an input output is happening after instruction 1. So after instruction 1, we want to do a write. Write means write something to maybe the printer or to the disk, which are very slow devices. So I'm going to go from 1, then I'm going to execute the write operation, which is 4, 5. Then I will go to 2, then there is another write operation. Then there is another write operation over here. Then I will go back. Now this is a very odd way, because these 4, 5 signals are very slow, and this means that the write operation will consume a lot of time from the CPU. Now the other method is to use interrupts with short waiting. Now the interrupts with short waiting will be running like this. So I will have to run the program. Once I reach the write, I will issue a write, and then in the middle over here, I will not wait. I will go back to my program, execute. Once the value over here is ready, I will go execute it, then I will go and continue my program. Again, once more, this is repeated. As you can see over here, I will do the first part of the writing, then I will continue my program, and in the middle, once operation 5 is ready, I will go and execute it. Over here I have to wait for all of them. So the time, as you can see, the time over here, which is this one plus this one, is the same as the time from here to here, but what we saved is the time of waiting between 4 and 5. This time of the input output command waiting, we did not waste it. Instead, we executed the part 2A over here. This makes the program much more faster. Here is an interrupt with a long wait where you have to wait. As you can see, the waiting time is very long. Here the waiting time is quite shorter. So you can see that we executed 1, we executed then 4, then we finished 2, then we finished 2, then we did 1, then we did 4, then we finished 2, then we went for 5, then from 5 we went back to 1, then we went back to 4, then we finished 3, then we went back to 5. Any scenario of these two will be much more faster than having this scenario with no interrupts, because interrupts can save us a lot of time, and interrupts can make things much more easier to deal with. So a program flow with interrupts will always be faster because there is no wasted time for the CPU. If something needs the CPU to wait, the CPU will be doing something else at the same time. And once that long or slow program finishes, then the CPU basically will go back and finish the thing as it is. Then we talk about the program timing. As you can see over here, when there was short interrupts, we did 1, then we did 4, then we did 2A here, then we did 5, then we did 2B, then we did 4, then we did 3A, which is 4, 3A, 5, 3B. In comparison, when a program has no interrupts, I will do 1, then I will do 4 and wait, then 5, then I will do 2, then we will do 4, 5, then we will do 3 once more. So this will take longer. This will take longer time. This will take longer time from the CPU. Again, once more, this example is with interrupts with short time waiting. You can see here, this is the short time waiting. This is with this is how the program ends up. Now, if we were doing a long wait, and our program will has longer time to wait. You see here, it's a short time to wait, so we could execute in that short time half of 2A, then half of 2B. So we broke down the program. But if it was a longer time to wait, as you can see over here, then we will do 1, 4, we will wait for some time, then we will do 5, then we'll do 2, so we'll do 1, then 4, then 5, then we will do 2, then 4, then 5, and so on, and there's a waiting time. Now, if it's like this, we can do with interrupts. We will do 1, 4, 2. We will have a wait, yes, but this wait will be smaller in comparison to this wait, and the end program will be much more faster, and the result will be much more better in terms of time needed to execute the program. Now, sometimes you have multiple interrupts, and sometimes interrupts, they overtake the actual CPU. So we need to disable the interrupts. For certain applications, we need to disable the interrupts. So the processor sometimes will ignore further interrupts while as processing one interrupt. The interrupts remain pending and are checked after the first interrupt has been processed. Interrupt handler are handled in a sequence as they occur. So sometimes also we define priorities for interrupts. Some devices, they require interrupts, but they are not important in comparison with other devices. So we define the priority. Low priority interrupts can be interrupted by higher priority interrupts. When higher priority interrupts has been processed, the processor returns to the previous interrupts, as you can see over here. These are the sequence of interrupts. You can see that we have a program, we have interrupt X and we have interrupt Y. So after interrupt X is being executed, we handle interrupt Y. This is called sequence. Even though maybe Y has higher priority than X, but Y cannot interrupt X. The other method that Y can interrupt X while X is interrupting the program, because Y has higher priority than X. So if the interrupt program is handling Y and at the same time an interrupt is requested by is handling X and an interrupt is being presented by Y, then it's quite straightforward. We are going to interrupt X and handle Y, then we go back to X, then we go to the main program. These are just formalities and how things are going. So you can see here we have our user program. At t equal to 10, a printer ISR is requested. In the same time, inside the printer, a communication is happening, then a disk is happening. Remember, the disk and communication are higher priority in compared to a printer, so they can interrupt the printer program, which is interrupting the user program. So these things happen. For us as users, we don't see the difference very much because these things are happening very fast. These are in the nanoseconds, so we don't feel them, but this is how a computer is organized inside it. Now, the CPU structure, let me check here. Okay, the CPU structure, I will continue it in the next section, inshallah, at 1 p.m. So now we can take the questions if you have any questions.